What specific problem does Genius aim to solve, and why is this significant in the context of existing methods for enhancing reasoning capabilities in LLMs?
Genius aims to solve the problem of enhancing the reasoning capabilities of large language models, LLMs, without relying on any external supervision, which is a significant limitation of existing methods that typically depend on supervised fine-tuning or reinforcement learning with ground truth answers. Existing approaches often face challenges in generalization due to the need for well-annotated responses or the complexities of training generalized reward models, which can be costly and prone to reward hacking. By utilizing a self-training framework that generates responses from unsupervised queries, Genius allows LLMs to self-improve their reasoning abilities efficiently. This is particularly significant as it enables the model to leverage abundant general data, achieving notable performance improvements across diverse reasoning benchmarks, thus pushing the boundaries of reasoning scaling laws. Ultimately, Genius represents a novel approach that circumvents the limitations of traditional methods, making it a pivotal advancement in the field of LLM reasoning enhancement.
How does the proposed method, Genius, work? Illustrate the step-by-step process of how responses are generated, rewarded, and optimized in this framework.
The proposed method, Genius, operates through a self-training framework that enhances reasoning abilities without external supervision. First, the policy LLM generates responses based on a set of unsupervised queries. These responses are modeled as sequences of steps, where Genius performs stepwise sampling to derive the globally optimal response by rolling out candidate steps and simulating future steps to calculate foresight scores. Next, Genius rewards these responses by selecting optimal steps based on their foresight scores, creating preference pairs for training. Finally, the LLM is optimized using an advantage-calibrated loss function, ACO, which penalizes inconsistencies between foresight scores and step advantages, thus improving training stability and performance. This iterative process allows Genius to self-improve reasoning capabilities effectively, using only general queries.
Can you provide a simple yet detailed example to explain how the foresight resampling technique operates in Genius? Walk through a hypothetical scenario illustrating its main steps.
In the Genius framework, the foresight resampling technique operates through a structured process of stepwise sampling and evaluation. For instance, consider a scenario where the LLM is generating a response to a query. At timestamp K1, Genius maintains m preceding paths, each consisting of K1 steps. It then rolls out n candidate steps A_k for each beam, resulting in m times n total candidate steps. Each candidate step undergoes a foresight simulation, where future steps are predicted based on the current candidate, allowing Genius to derive foresight scores, F_k, for each candidate step by averaging the log probabilities of the remaining steps. Next, Genius normalizes these foresight scores to create a distribution, F_k, from which it samples to select the next step, A_k_m, for exploration. The selected step is then used to construct the complete response sequence, T_k equals A_less than k, A_k, A_greater than k, \closing parenthesis dot. This process not only facilitates exploration of diverse responses, but also enables the model to exploit the best performing sequences for optimization, ensuring a balance between exploring new possibilities and refining existing knowledge.
What are the theoretical or practical benefits of utilizing Genius over traditional methods like supervised fine-tuning, SFT, and reinforcement learning approaches in terms of performance and efficiency?
Theoretical and practical benefits of utilizing Genius over traditional methods like supervised fine-tuning, SFT, and reinforcement learning approaches include enhanced performance and efficiency in reasoning tasks. Genius achieves a notable improvement of over 7% in average performance across diverse reasoning benchmarks using only 25K unsupervised queries, while traditional methods often require extensive labeled data, which is costly and time-consuming. Additionally, Genius employs a self-training framework that allows LLMs to self-improve their reasoning abilities without external supervision, addressing the limitations of SFT and reinforcement learning that rely on ground truth responses or verification. The introduction of the advantage-calibrated loss function, ACO, in Genius further stabilizes training and boosts performance, demonstrating its robustness compared to SFT and other reinforcement learning methods. Overall, Genius not only enhances reasoning capabilities, but also offers a scalable and efficient alternative to existing approaches, as evidenced by its consistent performance across various benchmarks.
How did you validate the effectiveness of Genius? Discuss the datasets, benchmarks used, and the metrics that were applied to measure performance improvements.
The effectiveness of Genius was validated through comprehensive evaluations across various reasoning benchmarks, including GSM-8K, Math, GPQA for math reasoning, Reclore and Logica for logical reasoning, and Strategy QA and ARC Challenge for general reasoning. Additionally, general benchmarks such as AlpacaVal, WildBench, and ArenaHard were included to assess performance stability, while knowledge-intensive benchmarks like Wikibench, MMLU, and MMLU Pro were used to ensure the model maintained its capabilities post-training. Performance improvements were measured by comparing the average results across these datasets, with Genius demonstrating a notable enhancement of 7.43% in average COT reasoning performance on Llama 3. 1-8B instruct using only 25K unsupervised queries. The results indicated that Genius consistently outperformed strong baselines, showcasing an average advantage of over 2% across all evaluation benchmarks. This validation approach highlighted Genius's ability to enhance reasoning capabilities effectively without external supervision.
What specific results were achieved using Genius, particularly in terms of performance metrics across the various benchmarks, and how do these results compare with established baselines?
Using the Genius framework, Llama 3, 1-8B instruct demonstrated a significant enhancement in average COT reasoning performance by 7.43% with just 25K unsupervised training queries from the MagPi dataset. This improvement was consistent across various benchmarks, where Genius outperformed strong baselines by an average advantage of over 2%, particularly excelling in challenging tasks like math, where it surpassed the self-rewarding method by more than 4%. Additionally, Genius maintained performance stability on general benchmarks, achieving slight improvements in most cases, and effectively avoided catastrophic forgetting on knowledge-intensive tasks such as Wikibench and MMLU. The results indicate that Genius not only enhances reasoning capabilities, but also provides a robust alternative to traditional supervised fine-tuning methods, showcasing superior performance across all evaluation benchmarks. Overall, Genius establishes itself as a state-of-the-art approach in boosting reasoning abilities without external supervision.